Parametric families of distributions of direct importance and reliability. ഈ ഒരു പോർഷനാണ് നമ്മൾ ഇന്നലെ ബോർഡിൽ എഴുതിയത്. ഇവിടെ ഈ കാണുന്ന സാധനം ബുക്ക് തരുമ്പോൾ ക്ലിയർ ആവും. R of t is equal to f of t by f bar of t. Okay. R of t, small r of t, failure rate function. Okay. What is the form of the failure rate function? We have discussed in the last class, offline class. R of t equal to f of t by, we have proved that. Okay, f of t divided by f bar of t, or capital R of t, whatever be the notation. So this is a failure rate function, and for the exponential distribution, R of t is equal to lambda or theta. Okay, a constant. Use theta, it is we will use theta. If we use lambda, you can put lambda here. Exponential distribution has the constant failure rate. That means failure rate not depend upon time. Okay, that means independent of time. Failure occur independent of time. For example of such failures are failure due to jerking, failure due to over voltage, sudden failure, or failure due to stroke in the sense high voltage or high current, or damage occurred due to overstrength. Okay, stroke, then failure due to accident. Okay, so such type of failures are not depend upon time. It can be happen at any time. Okay, so that type of failures are the failures due to these causes are not depend upon time. So such a failure pattern can be modeled using exponential distribution. So what is the shape of the what will be the shape of, yeah, this one is the failure rate behavior constant. Here you can see lambda is equal to 0.002 failure rate function distribution. Exponential. This is a failure rate hazard function or failure rate function. You can call failure rate function as hazard rate function also. Okay, that is another name. It will be constant, that is not dependent upon time. But you know that in the last class we have discussed Weibull distribution. Okay, what is the failure rate function of Weibull distribution? There's a failure rate function of Weibull distribution. I think that is some alpha, right? Alpha പിന്നെന്തായിരുന്നു തീറ്റ അല്ലേ, ലാംഡ. ഒരു കാര്യം നമുക്ക് തീറ്റ നേടാം. ആൽഫ തീറ്റ ഇൻറ്റു തീറ്റ ടി അല്ലേ, തീറ്റ ടി റേസ് ടു ആൽഫ മൈനസ് 1. So this is the failure rate function of the Weibull distribution. So actually, what is failure rate? A component or a system, probability of a rate of a probability of a component or a system which have already survived it small t units, but it will fail in the next small interval t comma t plus delta t. So that small probability is called what is that, conditional probability, and the rate is called, the limit of that probability, that is rate of that probability, is called failure rate function. Okay, the formal definition is given in this book. That means first chapter, you can read that. So you can see other type of failure rate patterns here. It is decreasing, decreasing failure rate model. Okay, this is another let us look at a Weibull pattern. Weibull pattern. Weibull distribution pattern. Weibull failure rate. Yeah, this one is the Weibull pattern. We can have constant failure rate when beta equal to 1. That means in our case it is alpha. We have used alpha, so let us replace with beta. Beta. Here also we can use beta. Okay, you can use any parameter, no problem. So this is the, if beta equal to 1, so this is just the, what happens when beta equal to 1, this is just theta only, so that is the failure rate of exponential. So when beta equal to 1, the failure rate becomes constant. Okay, when beta is greater than 1, it will be increasing. We have discussed in the last class, since the coefficient of this lambda t raised to this coefficient will become positive, so that this function become increasing. But t square or t cube adakku nokkiya ariyam, adu increasing ആണ്. So t raised to a positive quantity will be increasing, so r of t will be increasing. And when beta less than 1, then the coefficient become negative, then this coefficient become negative. Beta is, suppose beta is 0.5, then 0.5 minus 1 is minus 0.5, so this will become negative. So the power of t is negative, that means t comes in the denominator. So as t increases, this term, entire term will be decreasing. So you can say that when beta is less than 1, it is decreasing. Okay. Another type of, so you have example of Weibull distribution. This is another example of another pattern for different values of parameter values. For different parameter values you can have this type of shape for the failure rate function. Okay, in the case of Weibull distribution, this is another pattern of Weibull distribution for these parameters. Okay, and you look at this figure. This is not for a Weibull distribution, this is a general figure. So what is the shape of this figure? This is nothing but a bathtub shape. ഇതൊരു ബാത്ത് ടബ് എന്ന് പറയില്ല, നമ്മൾ പറയുന്ന പോലെ ബാത്ത് ടബ് പോലെ ഉണ്ട് അല്ലേ. സോ ഇറ്റ് ഈസ് ബാത്ത് ടബ് ഷേപ്പ്. സോ if the failure rate function is of this form, then we call it as bathtub shaped failure rate function. Bathtub shaped failure rate function. Okay, what is this? Bathtub shaped failure rate function. My research area, or my research and my students' research, are focused on this bathtub shaped failure rate function. And Deepthi has already proposed 3 distributions with this particular failure rate. Okay, that is appeared in different journals and books. Deepthi. Okay, let us read. I will show you if you are interested. Deepthi. Desktop. You can also work in future on this area. Okay. Desktop. Okay, I will show you later. Books. In this book you can see the chapter 6 is advanced research in reliability and system engineering, stochastic models in reliability engineering, and it is edited by these persons. You can see look at this chapter 6, an upside down bathtub shaped failure rate model using dust transformation Lomax distribution, page number 81. This is upside down model, the reverse pattern of the bathtub shape. I will tell you what is this. Okay, this is the chapter. Look at this distribution. This is probability density. This is a new distribution developed by Deepthi, and it has upside down bathtub shape property. Okay, this is the density and property. Everything is look at this figure. Upside, first of all it will increase, then become constant, but in this case it is not become constant, but at the same time you can treat it as upside down bathtub shape, and then decreases. So a very little distributions are available with this shape. Okay. And another Okay, there are some research papers by Deepthi regarding on this what is that, upside down and bathtub shaped failure rate model. So this is bathtub shaped failure rate model. So you can have several distributions, and you can see what is the shape of this failure rate function. First of all, it will decrease. Okay, first of all it will decrease, then it will become constant, and then it will become increasing. So this period is called early life period. Early life period. So failure rate decreases. Okay. So this period is called useful life. Useful life. Okay. That means failure rate is constant, which is parallel to x-axis, and then it is increasing. It is increasing. Okay. This is wear out period. Okay. Failure rate increases with time. Okay. So this is the pattern. Yeah, we have several other images: decreasing failure rate, constant failure rate, increasing failure rate, and this is decreasing, then constant wear out. Okay, let us look at this distribution. Okay. So this type of curves are called bathtub shaped. This bathtub shaped എന്ന് പറയാം. വേറെ ഒരു മോഡലാണ്. This is also bathtub shape. Decreasing, then constant, then increasing. So first period is called early infant mortality period, and second period is called constant or useful period, and third period is called wear out period. Okay. A distribution having this shape is exponentiated Weibull distribution. Exponentiated Weibull. Exponentiated. Exponentiated Weibull distribution. That distribution has bathtub shape failure rate pattern. Failure rate pattern of exponentiated. I think this is for exponentiated Weibull. This is modified Weibull extension. This is also called a bathtub shaped failure rate pattern. Here we have bathtub shape. I think this is the pattern of exponentiated Weibull. Yeah, beta exponentiated modified, beta exponentiated modified. So you can have some distribution with the bathtub failure rate models. Okay, failure rate pattern. Okay, so I think that is sufficient for today's discussion. You can go through the for getting more failure rate pattern examples. Now suppose that in the last class we have attained a what is that equation like this: r of t equal to equal to limit limit delta t tends to infinity, so sorry 0, then what is that, 1 by delta t, right, delta t into, then we had in the blackboard we have written that f of t plus delta t minus f of t divided by 1 minus f of t. ഇങ്ങനെയായിരുന്നു നമ്മൾ ഇന്നലെ എഴുതിയത്, ബോർഡിൽ എഴുതി ഓർമ്മയുണ്ടോ? ആർക്കെങ്കിലും ഓർമ്മയുണ്ടോ ഇന്നലെ നമ്മൾ ബോർഡിൽ എഴുതിയത്? എഴുതിയെടുത്തല്ലേ? ഉറങ്ങാണോ എല്ലാവരും? ചോദിക്കാല്ലേ? ഗോകുൽ നിഖിൽ, ഇന്നലെ നമ്മൾ ഇങ്ങനെയാണ് എഴുതിയേ? എഴുതിയെടുത്തിട്ടുണ്ടായിരുന്നില്ല ഇന്നലെ? So this is so you can write like this, like put a 1 here, then it is same as 1 minus 1 minus f of t plus delta t. Okay, so you can divide with 1 minus f of t. You can consider this as a single function. So what will be the next step? It will be, you can divide, then you can see that this can be write like this, right? This will be common. Then what will be the next step? This we can write like f bar of, okay, bar neda, f bar of t plus delta t, and this we can write like f bar of t. Okay, so this is the formula. So what will be the, okay, you know that R of t will be, R of t will be increasing. Suppose this is increasing, what happens? That means f bar t plus delta t by f bar t increasing. Then 1 minus this will decrease, and then limit will also decrease. So when this increases, R of t decreases, and suppose this decreases, then 1 minus this will be increasing, so the entire function will be increasing. So you can state in terms of f bar t plus delta t divided by f bar t instead of R of t. Okay, so equivalently R of t increases when this decreases. Okay, R of t increases when f bar t plus delta t by f bar t decreases. And similarly, you can say that decreases, R of t decreases when this increases. Okay, using this equation. Using this equation, you can say that R of t increases when f bar t plus delta t by f bar t decreases, and R of t decreases when f bar t plus delta t by f bar t increases. So you can say the failure rate pattern in terms of this one. So what is the advantage of this function? This function need not require density, probability density, just reliability only. But R of t require probability density. So in the case of distribution is not having probability density function, or if the distribution is not differentiable, then we have to use this formula for the identification of failure rate pattern. Okay, if the density exists, you can use this small r of t. If the density exists, you can use small r of t. If density does not exist, then you have to use f bar t plus delta t by f bar t for the identification of the failure rate pattern. Okay, so that is the both equations give same information. At the same time, one can use when density exists and the other can use when density does not exist, or if the function is not differentiable. Okay, so when we use R of t, you can, sorry, ജീന ലീവ് പറഞ്ഞിരുന്നത്, സജേഷ് ഉച്ചയ്ക്ക് ലീവ്. Sure. So R of t exists if density exists or distribution function is differentiable or absolutely വേണ്ട അത് പറയണ്ട ഇത് മതി R of t exists. Okay. So in the case of density exists or distribution is differentiable, you can use R of t, otherwise you can use this one. Okay. So this formula not require existence of density, just use the reliability function or failure rate function only. Okay. So I think this is sufficient for today's discussion, and I will save this and I will send to you. You can use for writing the notes. Okay.